the difference in the distances to each foci is constant. This is different than an ellipse where it was the sum of the distances from each foci is constant. Here's what this means. So if this is my hyperbola, the definition says the difference in the distance to each foci is a constant. It's a set of all points that make that work. So when is a hyperbola used? Given any two fixed points with something fluid, you end up with something called a cant area, which is defined by, so like if you look at like electrical wires, that's called a catenary. And a catenary is based on the hyperbolic cosine. Okay, you guys all remember hyperbolic cosine? You remember me mentioning and your other anyway, that's one use of a hyperbola. All right, let's talk about how to graph these things. They look like this. The center is at HK for either one. By the way, your textbook mixes these up, calls this one A squared, this is B squared. It doesn't matter. It's as long as you... I like keeping the X, the H, and the A all kind of as one package deal, just for your notes. Same with the Y, K, B. When the X portion is positive, like here, whereas the Y portion is negative in this case, this will always be negative here, because squared squared, that has to be positive, so if we're subtracting it, that's going to be the minus part. If the X part is positive, this is how we remember it, it goes off in the X direction. Does that make sense? That's how I keep track of them. If it's positive for the Y, that means it goes off in the Y direction. If that helps. That was the only way I could remember it when I was taking these classes. Actually, let's start with a simple one. Oh, well, minus. We're centered at the origin here, right? I'm sorry, not origin. We're centered, yeah, at the origin. Pardon me. H and K are both 0 in this case. What is A in, in this case relative to our definition? It's 3, right? I'm going to go a distance in the X direction of 3. the y direction, how far up and down do I go? 1. The way we graph these is it's sort of the opposite of an ellipse. By the way, is this one going up and down or left and right? Left and right. We form a little box. The ellipse would go inside if it was a plus. A hyperbola is the opposite. It's hyperbolic. Extend the diagonals. I don't have time to get into why, but you trust me, right? These are asymptotes. Unlike some asymptotes, these asymptotes we do not cross. Now, unlike an ellipse, the major axis always tells us where the foci are. In this case, it's always what I call on the inside of the hyperbola. If it's left and right, it's going to be inside. If it's up and down, it's going to be inside. In this case, we're going sideways. And it never crosses. Some asymptotes do cross, right? Not these. But there are times when we cross the asymptote. Sometimes an infinite number of times. I can show you an example in a minute. The foci, c is equal to the square root of a squared plus b squared. I could get into why and all that, but again, oh, shoot. In this case, it's root 10. 3 squared plus 1 squared, or 9 plus 1. What is root 10? 3.1-ish maybe? So in this case, the foci, let's use root. Okay, can you do root 10 and tell me what you get? 3.16. 3.16. About 3.2. So that's going to be really close there. Right? Because this is 3 and then 0.2. It's because this one's very narrow. The wider it is, the further out the foci is. The same with a parabola. How are we doing? What are the x and y intercepts in this case? -3, +3 for the x-intercepts. How about the y-intercepts? There are no y-intercepts. This is no man's land here, right? Now, if these were switched, it was y squared minus x squared over 9. All of the red would be identical. The only thing that would be different would be here and here. Fair enough? And the foci would be down here and up here. And what?
And there would be a y-intercept.
And there would be a y-intercept but no x-intercept. That's right. Any questions? Our first hyperbola. Okay. We'll do our break now. We'll come back. We'll do a little more of this and we'll start.